right? And then in example 3, as the limit x is approaching 0 on the function 1 on x, actually here we're going to notice that um, there is no limit. There's no actual limit because we are saying, um, let's look at this. Remember, limit is being approached from the left side or the right side. Here is 0. If we approach, this is our x-axis and this is our y-axis, you're going to realize that if we approach 0 from the right side, so we are saying, let's say if we approach from this side 0, let's say we are dividing 1 by 0.1, you're going to realize that the y-axis, the y value, our function is going to go up. The more we approach it in this direction, the more it's getting up. You get the sense? And if we approach it from this direction, we are also going to realize that the more closer we approach from the negative side, the value is not going to be that big. The value is going to go this direction. And how do we describe this? We are going to say, okay, as the limit x is approaching 0 from the positive side, our function, where is it going? Is it going big or is it becoming small? We're going to realize the more we get this side, our y value is going up in the positive infinity direction. And as the limit x is approaching 0 from the negative side, our function, is it getting big or it's getting small? We're going to see it's getting small, so it's going to be getting in the direction of negative infinity. You get the sense? So that's why we say there is no limit on this. That's why the calculator mostly, when we approach this and when we have a number divided by 0, that's why we end up calling, say, that function undefined. That's why the calculator said undefined or make error, because it's getting up at the same time it's getting down. And remember, the reason is because it can't be 0 because it can explode. So we have a vertical asymptote. And our x is equals to 0. That's our vertical asymptote. Here, it's called a vertical asymptote. This is the value that x cannot be. So we are saying x should not be equal to 0 in any way. We just approach it from different sides, which is from the left-hand side of the 0 and the right-hand side of the 0. Then we observed how our function is behaving. All right. Let's look at example 4. Let's look at example 4. The factor and simplifying type, where we need to do something extra and understand how we always deal with the limits with different strategies. Example number 4, factor. We have to factor, find the factor, and simplify. How does that gonna work? We're gonna see as the limit x approaches 3 on the function x squared minus 9 over x minus 3, right? If you look careful on this, we're going to see that our domain of x is restricted. So if you look careful, we can say x cannot be equal to 3. X cannot be equal to 3 in this direction, in this sense, because there is no sensible answer according to the previous example 3 that we did, when it becomes 0 or when it's approaching 0, something like that. We can also see that there is a vertical asymptote when x is equal to 3. There is a vertical asymptote there. But actually, is there a vertical asymptote? Let's find out. Let's look careful how this graph might look like. Because the first thing we need to do is to simplify this. We have to simplify this. And how do we simplify this? Definitely, we can factorize the numerator and say, as the limit x approaches 3, we're going to factorize that's the difference of two squared, so it's going to be x minus 3, x plus 3 over x minus 3. And then we can cancel this and this. Then we'll be left with the limit. Every time, make sure you don't forget to write your limit. Now we have x plus 3. Definitely look careful. Everything changes. From the beginning of the question, we've been told that x cannot be 3. So how are we going to deal with this situation? Actually, as x is approaching 3, definitely our y value is approaching 6, because that's going to be 3 plus 3. We're going to get 6 on this. And how does it look like? That's this is a straight line. That's a linear. It's something like this. So y is equals to x plus 3. When x is 3, when x is 0, we remember on a straight line, if we want to graph the straight lines, we always look for the intercepts. So here is 3. When y is 0, then x is going to be negative 3. So it's something here. So our graph is going to be something passing here as this. But remember with the limit that our x cannot be 3. So when x is 3, remember it's a straight line. When x is 3 here, what is happening up here on the graph? So that's important. So there is a circle there. And then after that point, our graph continues to go wherever it wants to go. That's how it behaves there. We can also look at example 5. I can call it maybe the last example I can think of for this time. Maybe when, as much as I want to simplify the topic for you of limits, we can realize that in example 5, let's look at example number 5. In example number 5, oh, okay, that's so much easier. As the limit x is approaching, let's say 3, u cubed minus 27 all over u minus 3, right? Definitely, we also have the same situation where we say our our u cannot be equal to 3, right? But we can simplify again by saying the limit, as the limit x is approaching 3. How do we do this? We use SOP. Same, opposite, or positive. Same, opposite, or positive. So which means if we factorize that cubic, the difference of cube on top, we are going to realize that it's going to be u minus 3. And then we're going to have a quadratic, which is u squared. And it's going to be 3u. And we're going to have 9. So the signs, that's what we use this. It's going to be the same. So the same, it means the same as the one we have in function, which is negative. And then, or they should be, so it's this, the same, right? Then the opposite, which is the opposite of that, it's positive. And then all positive. That's what it means. So then all over u minus 3. If you want to understand how to factorize cubes, please, you can check my other videos. I'll send the link in the bio. Right. So this simply means this and this will cancel. And when those two cancel, we're going to have now our function as the limit x still approaches 3. Now our function is u squared plus 3u plus 9. How do we get the value here? So the easier way of doing this and finding the value we want is what we're going to get. Definitely, we're going to realize that our limit, actually, our y value is going to approach the value 27, right? 27. How is it 27? We're gonna have 3 squared here, that's 9. 9 plus 3 plus 3, 3 times 3 here, that's 9 plus 9, that's 3 times plus 9 plus 9 plus 9, that's 27. And graphically, how is it gonna work? Graphically, how is it gonna work? If we are to deal with this, something like that, and do we have roots here? Definitely, we might not have roots. What will be our turning point? So we're gonna have the turning points, something like, remember, x is equals to negative b over 2a. So our negative b is negative 3 over what are we gonna have? What are we gonna get? 2 over our a is 1, so it's gonna be negative 3 over 2 there. That's what we're gonna have. That's on our turning point. Our turning point is negative 3 1 2. So it's gonna turn somewhere here, and it's a positive, so 0 here. If you find the y-axis, definitely it's gonna be somewhere in this line, and it's going something like this. That's how it's gonna go, something like this. And when x, we have told that x is not supposed to be equal to 3. So when x is 3 here, what happens to the graph? It's the same thing. There's gonna be a hole on the graph. There's gonna be a discontinuity on the graph at this point, 327. Do you get the sense? That's how our graph is gonna behave in this particular moment. Oh, okay. Let me look at the last thing that I might want that's a little bit tricky on example number, let's say 6. So on this example number 6, we are going to realize that on example number 6, we are going to realize that sometimes we have to manipulate our systems so that they will be easy, but they have to be very, very mathematical, and they have to be sensitive. So I'm going to explain to you why we do this, and it's going to make it's going to make us to be in a better position to evaluate some of the limits. So we're going to say as the limit, x is approaching, let's say, positive infinity, our function, which is x squared minus 4x plus 3 all over 2x squared minus 7x plus 6, right? How do we deal with this? So the first step when we have something like this, to make it more easier, is to divide everything by the highest power of x. We have to divide every term by the highest power of x, right? Very good. Okay, it's fine, students. I will explain to you why we have to divide everything by the highest power of x. What I mean is, let's just do something like, as the limit x is approaching positive infinity, the highest power of x is x squared. So I'm going to divide every term by x squared. So I'm going to have 1. 4x divided by x squared is going to be 4 over x plus 3 over x squared. All over, that's going to be all over 2, right? That's going to be all over 2, and that's going to be minus 7 over x plus 6 over x squared. So look, using our previous understanding, as the denominator is getting big, we are approaching x with a positive infinity value of x, so which means this x is getting bigger and bigger every time. What happens to the functions on top? So definitely every rational thing is going to approach 0. So all of you know what's going to happen to this. It's going to be 0. It's approaching 0 as well. And this is going to approach 0. And this is going to be approaching 0. Get the sense? So definitely you're going to realize that as the limit x is approaching infinity on this function, our answer that's going to be left is half. So the reason why we divide by the highest power is to make sure that we are going to find out how each term is going to behave. Because when we approach the positive number, which is the bigger number, and if we create a rational from the previous examples 2 and 3, we realized that if we have a limit where x is approaching positive infinity on a 1 on x rational function, the bigger this value becomes and the smaller our entire function becomes. It approaches 0. So which means if this equation or if this function, our x is approaching the bigger value, what is going to happen is we're going to left with approaching an arbitrary value of half. That's what I'm trying to explain. Maybe you might want to see the how we can sketch this. If we have done how to sketch graphs, you're going to realize that if we look on top, we can factorize that on top. If we factorize the top value of our limit here, we're going to see if we factorize this, and it's going to be x actually minus 3, right? And the other one is going to be minus 1, x minus 1. Is that one? And we're going to realize as well that if we look on the denominators there, we're going to have here, if we find to factorize the new numerator, it's going to be 2x minus 3, I guess, yes. And then we're going to have x minus 2. So if we are to find the roots of these, do we have roots there? Remember, okay, let's have the graph, a sketch somewhere here. My graph is not looking good. My straight line is not really looking good. Okay, that's much better. Something like this. Remember, it's approaching half there, and if we y is half, which means it's not going to be half, but it's going to approaching half. Therefore, we have when y is equals to half, we're going to have an asymptote there. This is the line y is equals to half here, because remember our thing is approaching there, and our function is approaching that value. And here, if we say is equals to 0 on the denominator, we're going to have positive 3 over 2. So here, for avoiding 0, the denominator will be 0. We're going to approach positive 3 over 2. So we have an asymptote there at positive 3 over 2. And our denominator cannot be equal to 2 again. So we have another asymptote here at 2. To get the sense, our x cannot be 2 as well. If our x cannot be 2, I'm just dealing with the restrictions that my domain has, because if I look at the denominator, you can clearly see that in the entire function, I should not divide by 0. So to avoid that division by 0, definitely one of the values in the denominator, they should not be equal to 0. So we're going to realize 3 over 2 and 2. Here, this cannot be 0. If this becomes 2, then we have 0. That's why we have 2 here. And here, if we have 3 over 2, definitely this one thing is going to be 0. So if x becomes 0, everything becomes 0 and our function explodes. So we have that. And so which means our is the curve definitely on this function you're going to realize. So our function is going to approach half like that. Do you get the sense? Happens on the same way. Here it might be something like this. Yes, something like this. It approaches there here and approaches this, approaching this according to the guidelines we have. And we can clearly see that what will be our y-intercept and our x-intercept. And our x-intercept usually happens when y is 0. If y is 0, what's going to happen there? When y is 0, remember we have this half here at this point, right? And it's approaching that, so you're going to realize this as well. We have our x-intercept somewhere there, because it's also approaching this and approaching this. So yes, we know that it's also approaching this. So since it's coming up here, definitely it's going to come back to approach this, something like this. If you want to really see how this graph is going to be working for you, you are allowed, you can use what we call the Desmos calculator, the Desmos graphing calculator, the Desmos graphing um, calculator. It will help you to understand the graphs, and I think I'll make a video if possible for you guys. You can just comment in the section, so in the comments, give me the comments if you want to understand more about the graphs. But this is how our graphs works. So you can punch this in the Desmos calculator, and then boom, here you go. I think today we have spoke about all the limits that I try to explain how we can simplify and find the values that are being approached by the functions from the limits. I guess everyone is going to get a glimpse on how to simplify um, limits. And this is the best I can go, which is 1, 2, 3, 4, 5, 6 examples that I used for you. So this is the thing you need, and these are the skills you need, especially for students who are doing CAPS. I'm going to do again the video in continuity. Bye-bye.